Hello friends, welcome back to my channel. Today I will continue my discussion on distillation. This will be part 11 of that discussion, and today I'll be talking about simple distillation. I will discuss simple distillation. From now I have started discussing different types of distillations. Uh, Earlier in my earlier videos I have discussed flash distillation, and then I have also solved one numerical based on flash distillation. Those of you who have not yet seen those videos, I'm giving links to those videos in the description section. So today we will understand what is simple distillation, what is the governing equation for simple distillation, and how the governing equation is derived. That also you'll learn through this video. So let us begin the discussion. To begin with, let us understand, let us introduce ourselves to simple distillation. What is simple distillation? Let us first understand. Simple distillation, this is a single stage batch operation. It is a batch operation that is carried out in a batch wise manner, and it is a single stage operation. Theoretically, if you have to describe it, theoretically you can say it is equivalent to an infinite number of successive flash distillation steps. So flash distillation I have already discussed. You please go and watch that video. So simple distillation, you can say that theoretically it is equivalent, or ideally it is equivalent to an infinite number of successive flash distillation steps. Infinite flash distillations occurring in a successive manner. So the net result is simple distillation. Okay, so that's why I'm saying simple distillation is theoretically equivalent to an infinite number of successive flash distillation steps. Now, in each flash distillation step, what happens? Let us understand. There is an infinitesimal amount of liquid solution that is flash vaporized. Infinitesimal amount of liquid solution is flash vaporized in each flash distillation step. So result of this flash vaporization, it due to the flash vaporization of an infinitesimal amount of liquid, it produces an infinitesimal amount of vapor. Then the infinitesimal amount of vapor is condensed to produce an infinitesimal amount of distillate. Okay, so you have infinitesimal amount of liquid solution. You are flash vaporizing it, which produces an infinitesimal amount of vapor, and those vapor, when condensed, they produce infinitesimal amount of distillate. Okay, the net result of all this, that means if you consider all the successive flash distillation steps, the net result is the liquid feed solution. The feed solution, it gets differentially distillate. Each time you have an infinitesimal amount of liquid solution getting distilled. Are you understanding it? So the net result, you can say the net result is the original liquid solution, original liquid feed solution, it gets differentially distilled, and that's why the simple distillation is also called differential distillation. The other name given to this operation, or the other name is differential distillation. Why it is differential distillation? Because uh, you can see in simple distillation, or in this type of distillation, the liquid solution is getting differentially distillated. Each time you have an infinitesimally small amount of liquid solution getting flash vaporized. Okay, that's why uh, simple distillation is also called differential distillation. So if somebody asks you why it is called why simple distillation is also called differential distillation, you can describe that in this way. Okay, so I hope this is clear to you. Theoretical differential distillation. So whatever we have just understood, the theoretical differential distillation. Theoretical differential distillation can only be approximated. You cannot carry out in actual reality. You can just go close to that. That's why I'm saying theoretical differential distillation. It can only be approximated. You cannot duplicate it exactly. It just can be it just only can be approximated. Okay, so theoretical differential distillation can only be approximated under real conditions. Okay, now let us continue further. Now let us understand the proper operation of simple distillation, how simple distillation is carried out. The feed in this case is, let us consider a binary liquid solution. The feed is a liquid solution containing two components, component A and component B. A is more volatile component out of A and B. A is more volatile component. Now you can easily understand what I mean by more volatile component. So A has a lower boiling point at a given pressure, and A has a higher vapor pressure at a given temperature. A is more volatile. So let us consider the operation. So this is a still in which we are going to boil this solution. Let this be the solution of A and B, and there is provision of heating the solution. So the operation is carried out in a still. Still is an apparatus where there is provision of heating a liquid solution. Okay, so you have a liquid solution containing A and B in it, and then the solution is containing A and B in it, and you are heating it. The resulting vapors, so you are heating it, and the resulting vapors, they will be rising up and they will be removed at the top. So you can see the vapors, they will be removed at the top, and after removing them at the top, they will be taken to a condenser, and then in the condenser they will be condensed to get the distillate. Okay, so this is a still. As I say, as I said, a still is an apparatus where there is provision of heating the liquid solution. Okay, so this is the liquid solution, that is feed liquid solution containing two components, A and B. A is the more volatile component. And these are the vapors, and this is the condenser, and you are getting distillate over here. Okay, so liquid solution of A and B, in which A is more volatile component, it is heated, vapors are formed, they are taken to the condenser, they are condensed, and you are getting distillate. Okay, so uh, this is continuously happening, and this will be continued till you get a desired composition in the distillate. You have to continue till desired composition is obtained for the distillate. Okay, then we have also understood why it is called differential distillation, because it is a combination of infinite number of successive flash distillation steps. In each flash distillation step, an infinitesimal amount of liquid solution is flash distilled. Okay, so that's why the net result is the entire feed solution gets differentially distillated. Okay, that's why it is also called differential distillation. Okay, Now let us understand the operation. The feed, as I said, is a liquid solution of two components, A and B. A is the more volatile component. Then feed solution is charged to the still. So initially, before starting the operation, the feed is charged to the still. So feed is charged to the still initially before starting the operation. The still is an apparatus, as I said, and there is provision of heating liquid solution in that apparatus. Okay. So after charging the feed solution to the still, now the feed solution is slowly heated to create a vapor phase from it. So it is slowly heated to get a vapor phase or to create a vapor phase from it. The resulting vapors, they are immediately removed as soon as they are formed. They are immediately removed and condensed. They are immediately removed and condensed, and you're getting the distillate product. Okay. Now during the initial stages of the operation, initially uh, F, let us say that F moles of feed solutions are charged to the operation, and let XF be the mole fraction of A in it. So when you start the operation, you have F moles of liquid solution in the still, and in that solution XF is mole fraction of A in it, the more volatile component, and the feed is slowly heated to create a vapor phase out of it. We have understood that. So during early stages of the operation, what happens? The resulting vapor phase is rich in A. Okay. So during early stages, the vapors that are obtained, they will be containing majority of A. And what is the reason for that? The reason is A is the more volatile component, so it is going to get vaporized first. Are you understanding it? That's why during early stages the vapor phase is rich in A. But as the operation proceeds, what is going to happen? The vapor phase is going to become leaner in A, poorer in A. So as the operation continues for some time, the amount of A present in A in the vapor phase, it is going to decrease. Are you understanding it? During early stages, no doubt vapor phase is rich in A, but as the operation proceeds, the vapor phase becomes leaner in A. Okay, you can easily understand. So we can say that as the operation proceeds, the composition of the liquid in the still, that is composition, amount of A and B in it. So as the operation proceeds, the composition of liquid in the still, it changes. So as the components are getting added to the vapor phase. Okay. At the end of the operation, when you have desired composition for the distillate, the operation will end. And what happens at the end of the operation? At the end of the operation, whatever liquid is left in the still, the liquid in the still, it the that liquid is actually transformed into what is called the bottom product. So at the end, when you stop heating, the liquid remaining in the still will be the bottom product. So let us say that W represents the moles of bottom product that is obtained in the operation, and XW represents the mole fraction of A in it, mole fraction of more volatile component in it. Okay. Now let us continue. Now in differential distillation, what is the case? The vapor phase is always in equilibrium with liquid from which it is created. What is the reason? Because ideally, theoretically, it is a combination of successive flash distillation steps, and in each flash distillation step, vapor phase will be in equilibrium with the liquid. Okay, so that's why I'm saying in differential distillation, the vapor phase is always in equilibrium with the liquid from which it is created. Now let us consider any time, and let at any time L be the moles of liquid in the still in the middle of the operation at a particular time, at any time rather. Let L represent the moles of liquid in the still. and X be the mole fraction of A in it, mole fraction of more volatile component in it. Now, a differential approach is used since we are saying that it is a combination of successive flash distillation step, and in each flash distillation step an infinitesimal amount or a differential amount of liquid solution is flash vaporized. So we need to use a differential approach to deal with this problem. Okay, so what is the approach? In that we are going to consider DL moles of liquid vaporizing to produce dV moles of vapors. Simple thing. You have differential amount of liquid. Let that differential amount be dl. It is vaporizing to produce differential amount of or differential moles of vapors. Let those moles be represented by dv. Okay, and let y be the mole fraction of A in it. That in the resulting vapors, let y represent the mole fraction of A in it, more volatile component. Okay. Now, if with this understanding, if you have to write total material balance for this particular situation, how are you going to write? dV moles that are formed or that are created, dV moles of vapor are produced at the cost of dl moles of liquid. That is, when dl moles of liquid vaporizes, dV moles of vapors are produced. So that's why I'm saying dV moles of vapors are produced at the cost of dl moles of liquid. So how to represent that? You can represent it like this: dV is equal to dl, but since dV are produced at the cost of dl, we need a negative sign. So I'm writing it as dV is equal to minus dl, and I'm calling this as equation number 1. Now, in the same way, you can write component material balance. Here we are going to consider the more volatile component, which in this case is A. So the component material balance now will be written, or first we'll understand this thing. Now Y into dV, whatever dV moles are produced, and those moles, Y into dV will be moles of A in the vapor. And this moles of A in the vapor, they are produced at the cost of d into dxl moles of A in the liquid. Differential amount of A uh, that is vaporized, it results in Y into dV moles of A in the vapor phase. Okay. So again, if this information has to be represented with an equation, we can write it like this. So Y dV is equal to minus dxl. Again, the quantity is same, but since in the vapor phase you are getting it at the cost of A in the liquid, we need a negative sign. So Y into dV is equal to minus dxl. Let us call this as equation number 2. Now here x and L, these are both are differential, both are changing as the operation proceeds, both are changing. So we need to use a differentiation. I'll just talk about the material balances we have just understood. First was dV is equal to minus dl, dV moles produced at the cost of dl moles of liquid. Then y dV is equal to minus dxl, y dV moles of L produced at the cost of dxl moles of A. So since x and L both are changing, I will have to use the product rule of differentiation. So I have y dV is equal to minus x dl plus L dx. Now what we will do, we are going to use equation 1 in equation 3. Now equation 1 is dV is minus dl. So on the left hand side of this equation, left hand side of equation 3, in place of dV, I'm going to use minus dl. So if I do that, I have minus y into dl is equal to minus x into dl minus x dl plus L dx. That is y into dl is equal to minus x dl minus L dx. that is y dl is equal to x dl plus L dx. So this negative sign, if you since every term has a negative sign, you get this equation y dl is equal to x dl plus L dx. Then what I do, I'm bringing dl term on this side, so it will be y dl minus x dl, that is equal to L dx. Next, I can take dl common on this side, on the left hand side, so it will be y minus x into dl is equal to L into dx. Then if I rearrange it, it will be dl upon L is equal to dx upon y minus x. Okay, so what can you say about equation number 4? Equation number 4 is a differential equation. What are the variables? Variables are x and L. What are the limits? Let us understand in order to solve this. So at the start, the liquid in the still is the feed solution. So when you start, when t is equal to 0, at the start, liquid in the still is the feed solution, and when the operation ends, at the end, the liquid in the still is the bottom product. So you need to understand these two facts. At the start, in the still you have feed solution, and at the end of the operation in the still you have the bottom product. So we are going to use this information to get the limits for solving differential equation number 4. Now let us understand this. Okay. So a differential equation, we have got it on previously. That was equation number 4. dl upon L is equal to dx upon y minus x. Now what are the limits? Uh, Again, I have talked about it. At the start, the liquid in the still is the feed solution, whereas at the end, the liquid in the still is the bottom product. So if you have to write it mathematically, you can say it like this. So at the start, when liquid in the still is feed, x is xf, the composition is equal to the feed composition, and at the end, when liquid gets transformed to the bottom product w, the composition also gets transformed to xw. Okay, so simple limits are at L is equal to f, x is xf, and at L is equal to w, x is xw. Okay, so we by using these limits, let us integrate equation number 4. So it will be integration from w to f dl upon L, that is equal to integration from xw to xf dx upon y minus x. Okay, so integration of dl upon L is ln of L with the limits from w to f, that is equal to integration from xw to xf dx upon y minus x. So if you use the limits, it will be ln of f minus ln of w, that is equal to integration from xw to xf dx upon y minus x. And now you can use the logarithmic identity. What is that? Ln of m minus ln of n is nothing but ln of m upon n. So we are going to use this logarithmic identity. So accordingly, we will be having, just a minute, I'll erase it. Okay, so accordingly you'll have ln of f by w, that is equal to integration of dx upon y minus x from xw to xf. Now let me call this as equation number 5. So equation number 5, this was derived by Lord Rayleigh, and that's why it is known by by his name. That's why it is called Rayleigh's equation. Okay, so Rayleigh's equation, you can say, is the governing equation for simple distillation or for differential distillation, as simple distillation is also called differential distillation. Okay, now let us talk about how we can solve the Rayleigh's equation. Okay, so the equation is ln of f by w is equal to integration of dx upon y minus x from xw to xf. Now you can solve equation 5 analytically if you know how y is related to x. So I'm saying equation 5 can be solved analytically if an expression for y in terms of x is known. If you don't know that relation, if you don't have that equation, in the absence of such an expression, what can we do? We can solve this integral. You can solve it graphically. You can solve the integral on the right hand side of equation 5 graphically. So how it is done, let us understand. The VLE data, that is XY data, vapor liquid equilibrium data, we need that data in order to get this integral graphically. So what is done? A graph between 1 upon y minus x and x is plotted. To be more correct, 1 upon y minus x is plotted on the y-axis and x is plotted on the x-axis. And whatever curve is obtained by this plot, we need to find area under the curve. Area under the curve, it is measured between the limits. What are the limits? X is equal to xf and x is equal to xw. Okay, this is one thing. I will show you the graph. Okay, so one option is, first option is, if you know the expression for y in terms of x, you can solve it. So you can simply put that expression over here and then solve this integral analytically. But in absence of such an expression, what can you do? You can solve it graphically. For that you need to know, or you need to have VLE data, XY data. And if you have that data, you can plot a graph where 1 upon y minus x is plotted on y-axis, x is plotted on x-axis. You get a curve. You measure area under the curve between limits xf and xw, and that area under the curve is nothing but this integral. Okay. And the third option available to you is, you can use any suitable numerical method for solving the integral. Okay, in my next coming videos, I'll be discussing numericals and I'll show you how you can solve this integral in various ways. Okay, so time being, let us understand we need to solve that integral and we have different options for doing that. Okay, so here I'm showing how you can do it graphically. So as I said, on x-axis you are going to plot x, on y-axis you are going to plot 1 upon y minus x. So you'll be getting a curve like this. You fix the limits. One limit is xf and the other limit is xw. So you get this region. So you need to measure this area under the curve, and this area under the curve is nothing but the integral dx upon yx from xw to xf. Okay, so that means when you have the Rayleigh's equation, ln of f by w, that is equal to the integration from xw to xf dx upon y minus x. So now by this way you are getting the different integral, and then f will be known to you. When you measure the area under the curve, this integral will be known to you, so the only unknown will be w. Okay, so in this way, or this step will help you in calculation of w, and then using the total material balance, that means original feed solution was converted to distillate and bottom product. So you know f, you have calculated w. Now you can tell what is the value of d. Okay, so in this way you can use Rayleigh's equation. Okay, so with this I end my discussion for this video. Here I have told you what is simple distillation, why it is also called differential distillation, what is the governing equation, how to derive that governing equation, and then how to solve the governing equation, Rayleigh's equation. In my next video, I'll be discussing a numerical based on this. For now, thank you for being with me. Please subscribe to my YouTube channel. Continue watching my videos on my YouTube channel. Do subscribe to my channel. Tell your friends to subscribe to my channel. Hit the like button if you really like my videos. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Thank you. Bye bye.